already discussed. Okay, and then having the equivalent static loads defined. Okay, and then the response spectrum needs to be defined. Okay, then is the analysis and the responses. Okay, so from the analysis, we'll be getting a lot of results in the form of tabular outputs or GUI outputs in the form of graphs, right? That we had seen some of the graphs in the previous class for the static load cases, right? For the equivalent static analysis, where we had seen some of the story shears and the displacements, right, and the drifts in the form of
Yes.
a graph,
Yes.
right? So similarly, we can we'll be getting a lot of results from the dynamic analysis as well. Okay. So now, when we now in the modeling aspect, I had not gone into the property modifiers thing in the previous sessions, right? So for performing the dynamic analysis, IS 1893 tells us to assign uh, crack section properties for the columns, okay,
Yes.
and the beams,
Correct.
right? So this thing can be integrated in the model in two ways. One is, while defining the frame section, there is an option for property modifiers. We can apply these property modifiers there itself. Okay, in that case, what will happen? All the frames that will be drawn for that particular section property will have those property modifiers, or else we can do that externally, right? So I'll just give you an example how it is done. So we'll go to define. This is the first way to define the property modifiers. We'll go to section properties and frame sections. Now we'll open, say, any one of these frame sections that are being used in the model. Say I'm opening the section property for the columns. Now here you can see that there is this property modifiers button over here. Okay, so currently it's default. Everything is defined as 111. Right, we can now say for this we can now define the say property modifiers here itself. For the columns, we have it as 0.7. Okay, so moment of inertia about both these axes will be 0.7. Okay, and I can press. If I press OK, it will be defined for all the frames of this particular section property, right? Otherwise, there is another method of assigning it externally. In that case, what needs to be done is I'll have to select all the columns. So I'll go to the select menu over here and go to object type. I'll select the columns. Okay, so all the columns here have been selected, and this method is actually useful because a live project will have different columns. Okay,
Yes.
there might be different column sizes, so
Correct.
defining them for each frame section might be a tedious job. So
Hmm.
now once we have selected all of them, we'll go to assign. Now in the assign the frame, it will be property modifiers, the second option. Now in this property modifiers, we can assign the crack section properties for these frames. Okay, now you can see here in the 3D view that PM has been applied. Okay, the property modifiers have been applied. You can right click on any of these frames here and check what has been applied. So in property modifiers, you can see that I22 and I33, they are set as 0.7. Okay, so this is one way. And then now for the beams, what we need to do is we'll go to the select option, right? And then we'll go to the object type, and object type will select the beams. Okay, and then again the same exercise, we'll go to assign frame and property modifiers, and in this case it will be 0.35 for the beams. Okay, So now we can see that property modifiers have been assigned to the beams as well. Okay, now this property modifiers can be even applied for the walls in the similar fashion. Okay, we just need to select. We need to select the walls, but in this case, we'll go to assign. We'll go to shell. Okay, and this time it will be the stiffness modifiers. Okay, now as per the codal provisions, whichever say bending direction or membrane direction, the property modifiers need to be applied. We need to apply it there. Okay, so I hope this is clear. So next is now definition of a flexible flow diaphragm. So basically, this flow diaphragm check can be uh, carried out by after getting the results. Right after you get the results, we can check. We can take the tabular output in Excel and check whether whether the clauses stated in IS 1893 is valid or not, and then we can go for a change in the diaphragm property. Okay, I'll come to this again. Okay, once I do the analysis, okay, I'll come to this thing again. Right now, what are the things that is available in ETABS for the linear analysis? We have the equivalent static method that I have already demonstrated in the previous class, and this class will be doing the dynamic analysis. And we also have the response spectrum method, we have modal time history method, and the time history method. And these are the the nonlinear analysis options that is available in ETABS, and that is a very comprehensive procedure. Okay, so we have horizontal shaking in the form of the IS 1893 response spectrum response spectrum plots. Okay, we have for this we use this spectra for the equivalent static method, and for the response spectrum method, we use this graph here that is specified in the code, right? And these values are computed through this through the horizontal seismic coefficient formula given in the code, the 0.5 formula, and we have and the acceleration is then converted into base shear by the seismic mass. Okay, and this base shear is in turn distributed along the height of the building by this quadratic distribution over here.
Yes.
Okay. This is done internally in ETABS, and the minimum design earthquake lateral force, that check is also performed. Okay, so I'll just come to the definition of the response spectrum curve first. Okay, so again, anything that needs to be defined, you can find it in this define menu. Okay, this time we'll go to functions, and the function will be response spectrum, right? So from this list, we need to come to IS 1893 2016. The Now we also have 2002 if
Okay.
someone needs to export that as well, right? So now we'll add a new function. You can see the response spectrum curve over here, and once you scroll on the graph, you can see the values are being shown for say different time periods. The time period is shown in the x-axis, and the y-axis it's the uh, is the spectrum
Spectral acceleration.
value. Yes, the spectral acceleration value over there. Okay, and this is scaled. This graph is scaled by the factor of g.
Okay.
Okay, and you can check it. You can check the acceleration here as well. Okay, in the form of say values over here, numerical values, right? Okay, so here we'll define a response spectrum, the horizontal response spectrum. Okay, so I'll name it say 1893 XY, right? And the seismic zone, you can see that for different seismic zones, the values will change. So I'm currently working with seismic zone 5, so I'll keep it as 5. Importance factor can also be varied. You can see the values will automatically change if I change the importance factor, right? Similar case with the response spectrum, response reduction factor, right? And the soil type also. Okay, I'll currently keep it as soil type 2 and response reduction factor 5, importance factor 1. Okay, right. So this is how we define the horizontal response spectrum function.
Correct.
Okay, and there is now the code also stipulates that for structures in zone 4 and 5, we need to consider the vertical shaking as well.
Hmm.
So we need to see that also the how the vertical function is defined. So in that case, we'll now go to the user menu,
Okay.
the user function, right? We'll add a new function, okay, and I'll name this 1893Z. Okay, and as per the damping ratio, okay, of the structure, we can,
5%
we'll
is best.
yeah, currently we'll go with the 5%
Hmm.
damping ratio. Okay, and now the code tells us that the vertical acceleration will be
1/3.
two-third of z by 2 into 2.5 divided by r by 1. So in this case, the zone factor is 0.36. Okay, so it becomes 0.36, 0.5.
2.5 by
It
3.
becomes 0.0. Yeah, it becomes 0.06. Okay, for zone factor 0.36, importance factor 1, and response reduction 5. The value is 0.06. So I'll now define it. So period I'll give as 0. The value will be 0.06, right? And I'll give an arbitrary period over here, say 50, and the value will be 0.06. Okay, you can see that the graph here is defined now. Okay, okay. So this is how we define the response spectrum functions. So the next slide. Now analysis types and definition in ETABS. We have seen the mass source, okay, how it is defined. We have seen the equivalent static seismic loads, the time periods. We can go for, say, the program calculated. Okay, in some structures we need to go for program calculated as well, and for the others will calculate as per the codal provisions, and the factors and the coefficients as per the codal provisions, how it changes. Okay, and we have also seen the auto and the user lateral load. Okay, and in modal analysis I have shown eigenvector analysis till now.
Hmm.
Okay, the eigenvector analysis, but the rich vector analysis option is also available.
Hmm.
This vector is very useful for getting all the displacement properly,
Yeah.
better than the eigenvector.
Hmm.
Okay, so I'll show this also. Okay, I'll show this now. Spectrum functions, horizontal and vertical. We have seen how it is defined,
Hmm.
and spectrum load cases also. I'll show it now. Okay, so modal analysis, widths, and horizontal and vertical spectrum load cases. So now anything that has to be defined will go to the define tab. Okay, now in this case I'll come to load cases, right? So modal is set as eigen currently. By default it is set as eigen.
Okay.
So I'll go to modify showcase, right? See, you can see that it's already defined as eigen, right? So in this case, what needs to be done is the nodal case type needs to be changed from eigen to ridge.
Hmm.
Okay, and say I need now I need all the three. I need the accelerations in all the three directions,
Hmm.
x, y, and z. So I'll add three tabs here. Okay, the load type will be acceleration. Okay, and the load name will be ux, that is translation in the ux direction. Okay, then the next will be acceleration along uy direction, and the third will be acceleration along the uz direction, right? And I'll keep the number of modes as say 1, 2, 3, 4, 5, 6,
12
7,
stories.
8, 9, 10, 11, 12. 12 stories, so I'll keep it as 36. Okay, a minimum number of modes will be 1, right? So now
So in
your
grids,
ridge.
you need to have all three. But if we are doing eigen, we need not to define this.
No, actually, if you need, you can also eliminate Z also if you feel like. Okay, but
Okay.
that makes no sense. If
Hmm.
you include the Z,
Spectrum, we are taking ME as in all three direction, vertical also. So we will take in all three.
okay, now you see that the menu changes. Okay, uh, I'll add a load type over here. Okay, the load type will be acceleration. The load direction will be U1. Okay, and the function will be that we have already defined for the horizontal cases. Okay, so this will be 1893 x and y, and the scale factor will be, you can see here there is an I button over here. Okay, the units for the scale factor column depend on the load type. Okay, and for acceleration or translational, it is in per second square. So we have it as 9806.65. This is by default there. Okay, and the modal case will be modal, and the modal combination methods we can change it as per the requirement. All right, directional combination type will be SRSS. Okay, modal damping as per the requirements 0.05, and diaphragm eccentricity. Now we can define a diaphragm eccentricity over here. Okay, say if the structure doesn't have any uh, asymmetry, we can go with the accidental eccentricity. In that case, we can go for say eccentricity ratio that will be constant for all diaphragms. We can go for a constant ratio. Okay, say 5%
So
eccentricity. Okay, or we can say if there is some asymmetry in the structure, we can always calculate the eccentricity for each diaphragm, and you know write it over here. Okay, in that case, the program will calculate the eccentric forces due to the earthquake, right? And that is this design eccentricity over here, right? This ESI, this ESI thing needs to be calculated separately. Okay, we'll look into that how this thing is calculated separately. Okay, we can get outputs for the diaphragms by the center of mass and the center of rigidity. Okay, and there in an Excel sheet over there, and we can just type the eccentricity over here for each diaphragm.
it won't matter if we are using
Okay,
rigid or flexible. ESI
yeah,
calculation will remain rigid or flexible diaphragm which we are using. ESI will remain the same.
yeah,
That
yeah,
is
yeah, yeah,
based on loading.
yeah. That will depend on the stiffness of the
Hmm.
structure and the arrangement of the structure.
Hmm.
Okay, all right. So currently, what I'll do is I'll keep it as 0.05 constant for all the diaphragms, right? Okay. So RSX has been defined now. I'll use the add copy of case and define RSY. Okay, this is also response spectrum, and the function will also be the same. Everything will be the same here. Okay, now the third load case will be the uh, response spectrum along the vertical axis. Okay, so I'll add copy of the case. This will be RSZ. Okay. Oh, sorry. There's one thing that I missed out. This RSY will be U2. Okay. This. This needs to be kept in mind. For x-axis, it will be u1, and for y-axis, it will be u2.
Correct.
Okay, and for z, it will be u3, and the function will also change. It will become 1890 z. Okay, scale factor remains the same. Okay, so now we have defined the RSX, RSY, and RSZ in our model. Okay, I'll now close this window. So these two things, we have seen these two. We have seen the definitions of these two things over here, right? And we have seen how eccentricity can be added into the response spectrum method. Okay, except for the calculation of ESI. Okay, we see this is the mass source window where we define the you know the the parts of the dead and the live load that will be
Correct.
used as seismic weight. Okay,
Yeah, that
and
makes
this
sense.
is the window for the static loading. This is for the response spectrum curve definition, and this is for the load case.
More than all
Okay,
four.
yeah. So as we have seen here now, vertical earthquake shaking needs to be you know used for the analysis in zone 4 and 5. Okay, and for all these cases as well, if it is having vertical or plan irregularities, if it is rested on soft soil and structures with long spans, which cause amplification of oscillations due to the flexibility. However, this long span not defined. Structure as large overhangs of structural members or subsystems. Pre-stress structures, structures with pre-stress members. Okay, so we have defined the vertical earthquake component also, right? You can see here. Okay. Okay, now I'll just close this presentation and I'll come to the model. I'll come back to the model now. Okay, so we have now defined all the load cases that is required for the dynamic analysis. Right. So I'll go to analyze, set load cases to run. Okay, and okay, before I run, since the model has been imported from a higher to a lower version, just for a just for a measure of precaution, what I'll do is I'll go to the analysis advanced Sapphire options. Okay,
Okay.
I'll use the standard solver.
Okay.
Okay, uh, I'll go to now set load cases to run. If everything is done here now, everything is set to run. Run now. Okay, has everyone's model run?
You guys have made the response spectrum nodes. And what is it working?
Okay, so we can go to this analyze button over here, and we can check the last analysis run log. Okay, it shows us all the how much time it takes for running, and at what time the process has started, what time it ends. Okay, how much mode shapes have been found. Okay, if there are any instabilities, it will show here. Okay, see basic stability check for linear load cases. Okay, you can see all the runtime information over here.
Okay.
Right. If you turn on the standard solver, if, if there are any say errors or warnings in the model, that the exact information will be shown here. Okay, in which joint the problem is there. Okay, which degree of freedom is unrestrained and all that cases, all that things.
All right.
Okay, so it's always prudent to turn on the standard solver whenever we are working in a very complicated model, or where the time is of the essence. so that we don't get stuck into resolving the errors and the warnings. Okay, so now what we'll do is there will be multiple results now available. That we can go to say display option. Okay, now we'll go to the show tables. Okay, so once we run the dynamic analysis, we need to check whether the participation factors and all have been taken care of.
Correct.
Okay, we need to see whether the first three modes have excited 65% of the mass, and whether the total summation is also satisfied or not. So what we'll do is we'll go to structure output, we'll go to modal information. Okay, you can see a lot of tables have been created, say modal periods and frequencies. If you want that in a tabular format, you can check and see all the different modes here, its time period and the frequency. Right, this is in descending order for the time period and ascending order for the frequency.
Hmm.
Right. Okay, and similarly you can do is should say need to get more tables over here, you can go to add tables. Okay, again open this modal information, right, and modal participating mass ratios. Okay, then from this drop down menu, modal participating mass ratio. All right, so you can see over here that the first three modes have more than 65%.
Yes.
All right, and you can check your summation, it's greater than 90%, so the analysis is fine. Right, so now what I'll do is I'll check for the base shear. Right, I'll check for the base shear now.
Hmm.
Okay, so the same thing can be checked from structure output. Okay, this time I'll open the base reactions. Okay, and from the load cases, here I'll select I don't want all these over here. I'll just select them. I'll just select them over here. Okay, and I'll turn it on. Okay, base reactions. Right, now we can see over here. This is uh, RSX, and this
Okay.
is FX. Okay, we need to check the FX for the EX and the FX for RSX, and
Around four
similarly for
times.
EQY. Yeah.
Around four time difference is coming. No?
Yes, around four times. Okay, so that scaling needs to be done. All
Hmm.
right, so that can be done by unlocking the model.
Okay.
So we'll unlock the model over here. We'll again go to define, turn on the load cases. Okay, and here in the scale factor, we will apply this as, say it is 4.2. Okay, and again for RSY also it was similar, around 4.2. Okay, we'll again check the model now. We'll again check the results.
But if we do on load combination, will this be the same, or it has to be done on the simple load case only, not on the combination
Uh, this RS for the
scaling?
response spectrum.
Yes, that has to be done on
Response,
the individual case itself, or on the load combination. We'll see.
better you do it on the individual case itself. All right, uh, because that will be much more simple.
Hmm.
Because if you have a load combination, uh, it might get a little complicated, and you might miss it out in some cases.
But again, if I'll do even with the scaling, the load
Hmm.
combination now, I don't think so. Results will come same on the base shear value.
With this,
If I'll apply the
uh,
even the modified RS after
hmm,
applying
hmm,
the scaling
hmm,
factor and then doing a combination with RS versus doing with the static load case,
hmm.
there will still be, I guess, not the same result will be there of the base shear. I'll have to check. I can
No,
also see.
no, you'll get the base shear now. I think if you go to the flow tables option over here.
Now it will come. Yeah.
Yeah,
But I'm
yeah,
saying,
for a load.
yeah,
Okay, for a load, you're talking
combination.
about a load combination.
Yeah.
Okay, load combinations. I have not checked. I think if I check, I think you can just check it on your own also if
Yeah.
you get the
See.
result. All right, it might come same, but for a complicated structure where there will be a lot of response spectrum load cases having
Mm.
different combinations,
Mm.
you might miss it out.
Mm.
In that case, you'll have to create one load combination for dynamic X where the scaling is done, or say
Yes.
dynamic Y where the scaling is done, and use that combination in the other combinations.
Mm. Correct.
Okay,
This is the
so
easier way to see. Now you can show maybe
yeah,
here it is
it's an
also coming same.
this is a easier way to get it
Yeah.
scaled.
Yeah.
Okay, all right. So now there are a lot of other things that can be checked. We can go for this story drifts and all that. Okay, you can check the story drifts also, and okay, the diaphragm thing also can be checked whether you know this. You can check this clause over here. Okay, I'll just turn it off over here. Okay, um, displacements, story max over average displacements. Okay, I'll just turn it on. I'll take the EQX and the EQY. Okay, you can see here the ratios are calculated over here as well. Okay, the maximum and the average, their ratios are calculated. You can always stick it to an Excel file. Okay, you can go to the file menu, export current table to Excel. Okay, so your Excel screen over here pops up, right? You can see that you have the maximum displacement and you have the average displacement also. All right, and you have the ratio. Okay, and the other clause also needs to be checked. This okay, and this average. Okay, right. So you can make use of these values also. Okay, for some other checks as well.
Here we are getting the clause till 1.2.
Yeah, you can see here. It's the ratios are
1.26.
you know within limits over here. Okay, so this is a can go with the rigid diaphragm in this case. Okay.
Maybe we can show modes also if that torsion is not coming.
Yes, you can get the mode shapes also from the deformed mode shape option over here. Sorry, deformed shape option. So you can go to show deformed shape. Right, you can check the modes. You can see the you can start the animation here. You can see that this is a proper translational mode.
Mm.
And the second mode is also a proper translational mode. Okay, the third one is a torsional mode.
Generally, we avoid third also in torsion. No?
Yeah, generally that is also avoided.
First three.
Okay, yeah. So now to avoid that, you can always check the stiffnesses and vary the stiffnesses along the axis and avoid them.
Yeah. Mm.
Right. That is another different exercise.
Mm.
Okay. Okay. Now, if you just go to the last slide over here. Okay. Now see for you can see here for checking different things over here, we have the different tabs, right? For checking now, if you need to say check the soft stories over here, okay, we can always go for story forces or story stiffnesses, right? You can see from the from the show tables option here, you can check the story stiffnesses, then export it to Excel.
Then manually we have to see if it is coming
Yes,
in
yes,
range
you have
or
to
not.
insert the formula over here.
Okay.
Okay, whatever the code you know states for a soft story.
Okay.
Okay, that formula for this ki plus one greater than ki plus two. Okay, or ki plus one greater than ki. These formulas here need to be put into Excel over here, and you can check whether your soft story is there or not.
Okay.
Okay,
Directly it doesn't shows.
no, no, directly it won't show.
Okay.
Okay, then say for okay, for plan irregularities or torsional irregularity, we had had taken out the maximum displacement over average displacement table from ETABS. Okay, we can insert these formulas over here. Okay, and check whether there are some plan irregularities or not. Okay, similarly uh, for these re-entrant corners and all that. Okay, we can either check them through the formulas. We can check it through Excel and then modify it to a flexible diaphragm over here. Okay, and similarly for if you have an opening in the floor system. Okay, we can perform this similar checks and go for a flexible diaphragm instead of a rigid diaphragm. Okay, and for out of plane vertical offsets
Hmm.
in vertical elements, this is some other. This particular case will require some rigorous nonlinear analysis. Okay, that can be done in ETABS, and your linear analysis results may not be of much use in this case.
Okay.
Okay,
There
so
we will have contact non-linearity.
yes, we'll be having this. Uh, yeah, there will be multiple nonlinearities here that can be checked through the nonlinear analysis options. Okay, okay. Now for vertical irregularities, for checking a soft story, I had already, you can, I had already shown that stiffness a table that was available in the ETABS model. Okay, and for the vertical irregularities, now for checking mass irregularity, we can check it through two ways. You can go to say I'll go to add tables. Okay, there's this mm, mass data. Okay, we can have mass summary by story. Okay, in this case, it gives us the mass that is in kilogram needs to be converted into the weight, and you can check it from here by exporting it to Excel. All right, or else there is another method that can be employed. We can go to define. Right, I can say define a combination over here. Okay, this combination will be for the seismic weight. That is dead load will be 1, and the live load will be say 0.25, and I'll keep it as seismic weight. Okay, so I'll again go to the display show tables. Now, in this case, I'll turn that off. I'll go to structure output, other output options, and we'll check the story forces now.
Okay.
Okay, now I'll deselect all of them. I'll clear the load cases. Okay, one combo over here. Okay, okay, okay. Now you can see here the output case is seismic weight, right? And we have uh, the seismic weights over here. Okay, this can be taken to Excel, and we can check for the mass irregularity as per the codal provisions.
Okay.
Okay, in Excel.
Mm.
Okay,
Yes.
okay. Now for vertical irregularity and incline discontinuity, that can be done manually over here. Okay,
Mm.
that these things can be done manually. And for checking the strength irregularity, this again involves a rigorous nonlinear analysis where uh, the rebars for all the frame elements are defined. The frame or the wall elements are also defined, and we can check the strength ratios and get whether there is a weak story or not. Okay. Uh, Now, similarly for floating columns, uh, it is normally not desired in a structure,
Mm.
but if you have that, in this case also we need to go for a
No need.
non-linear analysis. Okay. Normal linear analysis won't suffice. Okay. So now we have already checked for this. We have already seen the table that gives us the information about the mass participation factor. All right. And we have also seen the modal frequency and periods table. Okay, where this thing can be checked. This clause also can be checked. Okay. Okay. So these are the tables that are required. Okay, for doing this checks. Okay, these are the particular tables. Okay, for mass irregularity, we'll be checking mass summary by story, or we can go to that. We can go to story forces by having by having a seismic weight load combination defined. Okay, and for the torsional irregularity, we can use even for this for story drifts. We can turn on this table story drifts. It will give us the details of the story drifts. Let's see that as well. We'll go to display, show tables. Okay, you can see over here.
Mm.
Okay, you can see the story drifts that are shown over here. Okay, this can be again. Okay, now sorry, this seismic weight is only being displayed over here. I'll just change it. Okay, just wait a second. Show tables. Go to the displacements, story drifts. I'll clear the combo. Okay, it's cleared. Right, we have the story drifts. Okay, that can be checked for story drift for the story drift limitation as per the IS code. Okay, by taking it to Excel. Okay, and we can just insert a simple formula and check. Right. Then for irregular modes, the participating mass ratios, and we can even check the the modal periods and the frequencies. And for the soft story, it is to be checked by the story stiffnesses. Okay, so these are the checks that can be done using ETABS. Okay, using ETABS and the output values that will be available in the form of an Excel table
But you have told that story drifts we can see also from that story menu which you were
from
showing.
story
The menu which you
from
were showing,
from the graphical representation, right?
graphical representation.
Yes, that is also available.
And that
You know
previously was
the
not there, I guess. That is being
Yeah, you can go to display. Instead of going to show tables, you can go to story response plots.
story response.
Okay, and in story response, we can select EQX.
Hmm.
Okay, we have the maximum story displacement over here. Now we can take maximum story drifts also.
Hmm.
Okay, and from here also we can get a table, right? This can be taken in Excel format.
Correct.
Okay, so results can be taken out from different
Hmm.
in
Either
different
from
ways.
report menu or from
Okay,
this menu.
yeah, you can even have it in the form of a report viewer for making reports.
Hmm.
Okay, and also have a detailed report over here where you have the table as well as the graph,
Hmm.
right? And this graph here can also be formatted. You
Correct.
can
I have a preset up.
can edit. Yeah, you can have it. You can set it up in different ways. Okay? You can change the colors and all that. You can also change the
Yeah. Now, if we compare like RS1 or ESX, which drift is coming better?
normally we use the EQX, the static
Static
case.
load case, yeah.
Yes,
We
yes,
have
the
now
static load
made it
case.
comparable, huh?
Because
So
yeah, because but it won't be the same actually.
here
See,
around we are getting 10.5.
yeah, you can see
It
it'll
is
be a
having
little
a lower.
different
Yeah, it is having a lower and a shape is
because
also different.
here uh,
It
the
is a
higher modes also will play the
participant.
role. Yeah, so your displacements will be highly exaggerated also. Okay, so we always check with EQX, right?
But why in y direction it is not showing as a VQX only? There it is saying in like X y direction also
Yeah,
it is
because in response spectrum,
yeah.
it is having some drift
Hmm.
along the X also because there are some there are some what do you
Torsional
say
motion.
torsional modes also,
Hmm.
right? So the participation of that is giving us this graph.
Correct.
Okay, so here now, okay, now for doing this ESI check.
Hmm.
Okay, there is another thing. Uh, okay, for doing the ESI check, we'll again need to go to show tables. Okay, uh, now here other definitions. Summary. I'll just check it once. Mm, Structure output. Displacements. Reference center of mass. So we'll go to other output items. Okay,
Okay.
we'll go to other output items. Here we have center of mass and rigidity.
Hmm.
Okay, I'll turn this table on and I'll transfer it to Excel. Is it open? Yeah. So now we can see here for each story and diaphragm. it gives us the value of the
Its location.
center of mass. Yeah.
Mm.
Okay. But the rigidity is not calculated. The option needs to be turned on before doing the analysis. Okay. I'll just check once.
You can show us where.
Yeah. But then you can calculate the eccentricity and to get it
Mm.
done. So just wait a second. Define. mm, Yeah. In this analysis option, okay, when you open the window, there is this diaphragm centers of rigidity, right? This uh, this this tab has to be switched on.
Okay, can we
Okay, then
get
you
it?
then you will get the diaphragm centers of rigidity. Okay, you need to run it now. Okay, now I'll just close all this Excel feature here. Yeah, we'll go to the display menu, show tables, and from structure output, other output items, center of mass and rigidity. Okay, now you can see that this XCR and the YCR
Correct.
values have come. Okay, and we'll go to file, export it to Excel. Okay, and the center of mass and rigidity, we can just have a simple subtraction formula over here, and
Instruments
just
section.
yeah, and just calculate the eccentricities.
Eccentric.
Okay, from here. Okay, so you can just do a simple formula over here, and you'll get the values, right? Okay. So this is the eccentricity, that is ESI. Okay, this now this ESI needs to be inputted into the uh, this when you go to the load case, the defined load cases. Okay, for RSX, we'll go to modify showcase. All right, and from here, diaphragm eccentricity. Say we have this now. Say for RSX, we'll apply the eccentricity along the X direction over here. Whatever values we have, okay, we can just can add it like this.
Okay, story by story we need to give.
Yeah, story by story, we can add it.
Oh,
Okay, and then once you save it, you will see that. Okay, sorry.
it is the same story. Yeah.
Yeah, yeah. I'll just give some arbitrary value over here, and when you save it, you can see here that there are some overrides.
Okay.
Okay, so now when you run the analysis now, your response spectrum load case will have the eccentric forces as well. Okay, so this is the apart from the accidental
Hmm.
torsion.
Hmm.
Yeah, so this is how the dynamic analysis can be carried out. Okay, for the linear dynamic analysis can be carried out in ETABS.
It is
Okay,
taking 0.05 plus 1 for story 1 or 1 as the final value, like what we
which
have
one?
given
Which one?
currently. Currently,
Which one?
for story 12, we are given say E equals to 1. So it
Yeah.
is taking
Okay.
0.05 plus 1 or it is taking
Yeah.
1
No. No. It will be taking one for story 12. Okay.
for rest of the
For all
story, it is only 0.05.
it will be taking 0.05.
Oh,
Okay. 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 So, all right. Now, coming to the coming to the 30% combination rule that the code tells us. Okay, for the response spectrum analysis cases. Okay, how do we incorporate that into the analysis model?
hmm.
Fine. Uh, Now this thing can be done in two ways. One thing we can do is for the response spectrum, we can define the 30% combination itself in the load case.
Okay.
Okay, we can have it done in this fashion. Say we have
Point
this.
three times.
Yeah, now I'll add acceleration, say u2. This will be xy. Okay, and the scaled one needs to be applied here. Okay, the one that is scaled already. Okay, so say similar, so I'll use this. Okay, this will be 30%. Okay, and for u3, okay, it can go to z. Okay, and it will be this. Okay, only one thing here is that your only one problem here is that you won't be getting that now. For having that negative and positive combination, you'll have to, you know,
Okay.
change the
Again,
sign of the scale factor.
yeah. Again,
Okay,
you have to create it.
yes. You have to again say add copy of a load case.
Minus
Okay,
point three.
say this I have defined as all positive.
RS
Okay,
plus X.
or I can tell it like x plus
Y
y
plus Z.
plus z, right? This can be one load case. Similarly, I need to add a copy of a case and make this say minus y. So
Plus Z.
scale factor here will become
Negative.
minus 1.
Okay.
Okay, so this is one way of doing that.
Hmm.
Okay, now in this case, this there is one advantage that your default load combinations that are created in ETABS,
Hmm.
that will take this up as a load case and simply create all the combinations.
Correct.
Okay. Otherwise, the other method is to define it as a load combination. Okay. So now we'll come to the load combinations.
Hmm.
Okay. So defining load combinations, again we'll go to the define menu. We'll go to load combinations. Right. Now I'll show how. Now you see that there are some default design combos available in ETABS. Okay, for your steel design, concrete design, composite beam design, shear wall design. All right, you can see here steel frame, composite beam, concrete frame. Okay, shear wall, concrete slab. So what I can do is you can. I'll just take the say, concrete frame design and you can also make it convert to user combinations. Then you can edit it. Otherwise, what will happen is the default load combinations will be used again and again. Okay, even if you make some changes. So you can see here, as per IS 456, okay, the default load combinations are created over here. So if you want to see how these combinations are, you can always go to modify, and you can see here that this is for only the dead load case. The decon S2 is for dead and live, and S3 is for it's having the static earthquake force. Similarly, a lot of load combinations are created for different load cases, right?
It will create for
Otherwise,
response spectrum also.
yes, it has also created for response spectrum. Okay, you can see here it is also created for response
Okay.
spectrum.
RSY also, RSX also. It is created for them
Yes,
also.
yes. Okay, so now say if I don't want to use the default load combinations, I want to define my own load combinations. So what I need to do is I'll go to add new combo, right? Now here I can name a load combination, say 1.5 dead load plus 1.5 live load, right? And keep it like this. Scale factor will be 1.5 and this will be 1.5. Okay, and this is not an auto combination.
Hmm.
Okay, so similarly for the 30% combination rule, we can have a load combination in this format. Say this is RSX plus 0.45 RSY plus 0.45 RSZ. right? And this will be 1.5. We can add another load case over here. This will be, say, RSX. However, this has the other
Yeah, no
direction
issues. Yeah,
combinations
yeah,
as well.
no issue.
Okay, and we'll take RSY. RSY will be 0.45.
Hmm.
Okay, and RSZ
But each time to
will
manually
again.
make them, that will take a lot of time. Is there a faster way to do so?
There is a faster way. Okay, I'll just tell you how it can be
Okay.
done.
Yeah.
If you can make it once,
Hmm.
right? Using it faster is if you define it as a load case.
Okay.
Okay, if you define this particular combination as a load case,
Hmm.
okay, uh, and uh, and then the software will identify it as a load case and make all the possible combinations.
Okay.
Okay,
No, but
so
I'm
if you
saying
do,
about in general also. Say I'm making 50 load combinations.
yeah,
So
in
50,
general, I'll tell you one way
yeah,
how it can be done. There is an uh,
duplicator or
interactive
something.
there's an interactive database editor available in ETABS.
Okay.
Okay, which makes the use of Excel, and you can automate this also if you feel like.
Okay.
So here we have this say load combination. I've defined some load combinations,
Hmm.
right? So now we'll see what all is available in the interactive database editor. Okay, for in now see, as the name suggests, anything with edit will be found in the edit menu.
Hmm.
Okay, so in the edit menu, this is the interactive database editor.
Okay.
Okay, and now in interactive database editor, we have, you can see here the system data. Okay, the grid systems, everything is there in the form of a table.
Okay.
Okay, you can if you feel like, you can export them to Excel. Okay, you can see here what all is there. And this is similar to the show tables menu that was
Hmm.
demonstrated earlier. Okay, now you can, if you feel like, you can take it to Excel. See, you can take it to Excel if you feel like changing any of this data over here. You can change it here. Okay, you can, and say after you have done the edit, you can always call back the table from Excel by retrieve table from Excel. Okay, or if
Let's
you
let's
feel
make
like you're,
let's make it FE 550 something. Just one simple change.
yeah, okay. Now if that is not defined already,
Okay.
okay,
It has
like
to be.
for steel we have Fe 250 and we have Fe 345.
Hmm.
Okay, if some other grade of steel needs to be defined, that needs to
Hmm.
be already defined, predefined. Otherwise, it'll show an error.
No,
Okay,
HYSD 550 must be defined. No?
HYSD 550. Okay, we'll do that. We'll
Third
make
row,
this.
yeah, sixth
Yeah,
row.
yeah. We'll just copy this and paste it here.
Hmm.
Okay, now you can go to Excel. You can retrieve the table from there. Okay, you can see it has changed.
Okay.
Okay, now you have to do is apply to model.
Apply to model out. Acha, it is there.
Okay, now it has been applied to the model. You can
Okay.
go and check in the define properties menu. Okay,
Hmm.
and the material properties, you'll find that HYSD 415 as now
Great.
grade 500.
Alright.
Okay,
So
okay. So
quickly we
there are a
need to
lot of,
change materials. Quickly we need to generate loads. All of
yes,
these
yes,
things
yes,
can be
that
done
can be done.
actually.
Yeah. Okay. Now here, what you'll get is, say you have see, it's always better to have a, a naming convention when you're modeling.
Hmm.
Okay, say for your dead loads, you have a particular name. Okay, in the particular format, say your caps lock is on, or
Hmm.
you can use any method of naming. Say you can there are different naming procedures, right? You can have the first letter in caps, others in short, others in small. Okay, or you can have two words joined together where the starting alphabets are in capitals. A particular format needs to be followed.
Yes.
If that is followed for all the models, then we can create some typical load combinations that can be applied directly. Okay, say we have this. from load case definitions. Okay, we have the load combination definitions over here. Okay, I'll open this table and export that to Excel. I'll just close the Excel sheets over here. First. Okay, now you can see over here it is there in the form of a table. I'll export this to Excel. Okay, you can see here this is the format in Excel, right?
Hmm.
So if you have to create a load combination, okay, say you need to have a load combination. If it has say two load cases in it, there will be two rows used for that. Okay, where the first load case is there and the scale factor is there, appropriate scale factor. In the second line, you'll be having
Understood.
the other load case and the okay. You can create load cases in Excel also.
But
Okay,
the
but this
GUID
the GUID it can be that
left blank.
can be just you can leave it blank or you can just copy paste whatever is there in this. Okay,
No, but for the new case, GUID should be something
that
different.
that will that will not make much of a difference. Okay,
Okay.
if I just remove this, okay,
Hmm.
and I retrieve this file from Excel, okay, you can see and apply it to the model, okay, you'll see that there is no issue with it.
Okay, no error will come through it.
Yeah, no error will come for that. Okay, next time when you close this table and do some analysis or something like that, automatically it will generate some random GUID over here.
Okay.
This is not actually not very important. Okay,
Okay.
only thing is this format is important that
Hmm.
is available in Excel. If you
Hmm.
can, uh, say create one dummy load combination and then
Yeah.
work on that in Excel,
Hmm.
right? And keep the load case names same for all your
Yes.
models.
Yes. Yes.
Okay, then what will happen is you can use your user defined load combinations for running your design and all that.
Hmm.
Okay,
All right.
so this interactive database editing, it makes lives a lot. It makes the lives a
Easier.
lot
Yeah.
easier. Yeah, if you otherwise, manually defining load combinations, around 60 to 70 load combinations is a
Correct.
big task,
Correct.
right? All right. Otherwise, as I told you, you can always combine the 30% combinations in the load case.
Hmm.
Okay. In that case, what will happen? Say while presenting the presenting the design or submitting it as in the form of a report,
Hmm.
the load combination name will come as say decon S or decon S3 or decon
Yes.
S5.
Hmm.
Okay. In that case, it will not make much sense to the person who is viewing
I
it.
was checking. Yeah.
Yeah, so you can always have your own load combinations.
That
All
is
right,
better.
or if you are presenting it in the form of a report, you can always use the Excel sheet that will be generated from the interactive database editor.
Hmm.
Okay, in that case, your decon S1 or decon S2 will be shown
Explain.
properly.
Yeah.
Yeah, that will be explained. Okay, all right. So, and okay, now some other things that can be done, like we can also get a BOQ from this, say the weights, or you can also compute volume if you feel like. Okay, say if I uh, from the defined material properties, okay, I'll define M25. I'll change the weight to 25 kilonewton per meter cube. Okay, and now what I'll do is I'll make groups and I'll assign all the beams and the columns into that particular group,
Okay.
right? And even the slabs.
Yeah.
Okay. So I'll go to say define now group definitions. We had not seen this earlier. Okay. So in group definitions, there is already a predefined group that is named as all. It has all the elements. Okay. Now I'll add a group name, say column. Okay. I'll add another group, say beam. I'll add another group, say wall. add another one, slabs. Okay. Now what I'll do is I'll select object type beams. All right, and I'll select them and I'll assign them into groups. Okay, the beams have been selected. I'll add all the beams to the group beam. Okay, next I'll do is now these two windows can be run parallelly. Okay, I can select the columns. Okay, and I'll assign them to the group column. Okay, similarly I can select all the floors. I'll assign them to slabs. I'll select all the walls and I'll assign them to wall. Okay,
Group are
right
just
now when
faster
I
selection method.
yeah.
If you select a group, you can do faster selection of that particular entity.
Yes, we can do that. It's very useful when you work with let's say
Multiple
trusses.
sections.
Yeah, in trusses and all that, where there the web members and all need to be selected separately, and the top chord needs to be selected separately. In that case, and when where there are different sections, all right, it's very useful, for working in that case. Okay, now you can run the model. Now this button can be used for running the model as well.
In this case, how much advanced solver and basic solver will give difference? If you are
Okay,
giving
advanced
only
solver
linear,
and
yeah, if you are
basic
only
solver. No,
giving, yeah, linear structure,
actually, what happens is if you run it using the basic solver.
yeah,
Say now I think I might have defined some load cases which are creating some errors.
yeah,
Okay, in that case, what will happen if I show the log here? If I open the show log, you see what are the reasons for the error.
okay.
Okay, I can see here error bad function data. Okay, so this error thing will not be visible if you use the basic solver.
Okay.
Okay, if you use the basic solver,
We were using basic
uh,
only, na? Standard.
or you can use no, if you sorry, not the basic, the advanced solver. Okay, so that those minute informations about the errors or the warnings will not be visible.
In advanced.
Yeah, in advance.
Okay, in standard it is there.
Yeah, in standard solver, it's available. Okay, all
But
right.
I don't think that there will be a challenging difference in linear analysis between these two solvers.
Uh,
Amongst the results, say story drifts or say base shears.
no, 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 no. That will not be. That is standard solver is basically it gives a lot of details about where the errors and all are located. Right. So that helps in that case. Okay, I'll remove all the. I'll just turn off the response spectrum load cases currently. I'll turn them off. Okay. Go to run.
We were seeing
Okay.
the detailed report also beam by beam, which Lakshya was telling initially.
Yeah. Okay. Now in this case, I'll go to other definitions. Group data. Oh, sorry. It'll be mass data. Mass summary by group. Okay, you can check here. The self weights are available over here for each and every item,
Mm.
right? And you can divide them by the density in kilonewton per meter cube to get the volumes as well. Okay.
And then for steel, we have not defined, so that's why it's not giving the for BOQ of steel.
Yeah, yeah, yeah.
We have to
Okay.
give some defined commands for designing.
For designing,
Yeah.
yeah, designing it is a little. Uh, yeah, designing is a totally separate thing. Actually, designing will be like we have come to the analysis till now.
Mm.
Okay. Now, say if I need to design the say the columns or the beams.
Mm.
Okay, there is this concrete frame design button over here. Okay, we can run the design using this. Before we go to the design option, we need to check the revise the preferences over here. We need to check them. Okay, you can see the design code is IS 456 2000. Okay, all the different points are given here. Okay, you can check whether the material factor safety and all are properly defined. Okay, now since here we have considering the minimum eccentricity and the additional moment, okay, for slenderness, all this needs to be checked before you run, right? And before I run the concrete frame design, I need to select, say, I'll select the material properties M25. I'll check the overrides. Okay, you can see that the framing type is ductile. Okay.
What are these overrides?
These overrides are actually, say if I need to design a, say, a column. So what I'll do is I'll select this column,
Mm.
okay, and I'll check here view revise overrides. Okay, it gives us the design section whatever is there. Okay,
Okay.
framing type whether it is ductile or ordinary. Okay, and then the live load reduction factor as per the IS code, right? And the unbraced length ratio and all that
So this
details
is
here are.
calculating itself, or we have to give this as input?
This is calculating itself.
Okay.
Okay, from the charts available in IS 456, okay, at the last page, okay, from those charts, it is calculating these factors, okay, and okay, now if you just press this button, you can see the, okay, okay, wait a second, I'll just make it ready for design so that I can show how the design is carried out.
No,
Okay,
for design, then combinations are not needed.
no, combinations are needed. Okay,
Okay.
I'll remove the load combinations that I defined earlier. Okay,
Okay.
I'll use the default load combinations that we have here.
Okay.
Okay, define load cases. I'll remove the multiple things that we have here.
Mm.
Keep it normal lex. No, okay. X, Y, and Z. Okay. Now, say before you go for the design, you can always select the load combinations that are to be used for the design. Right.
Okay.
Then go to select design combinations. Right. Here you can see that the default load combinations are already there. Okay. Now, say if you have defined some of your uh, load combinations which you want to use for the design, that will be available over here. In that case, you just need to use this arrow to shift it from here to here. Okay, now I'll run the design. Oh, sorry. Before I'll run the analysis.
We not need not to give any the things like what bar to use or what size to use, and instead we generally give the maximum bar size is this much.
No, 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 no. That actually the design results that you'll get. No, I'll just show the. I'll just
Demand
show
and
how it is.
capacity in demand capacity terms only.
Design. I think Okay, just wait a second. Some load cases are not set to run. So,
Okay, now we can make everything to run.
yeah. Okay. So I'll run the design now.
It gives in for individual member then.
Yeah, it will give the uh, area of steel output for each and every individual members. Yeah, there you go. Okay, now say uh, here for the column, we are getting this area of steel over here, right? Now, if I just take the cursor to this column and do the right click, you can see a window pops up over here. Okay, this is the concrete column design information. Okay, now here we have three buttons. We have the overrides button over here. Okay, you can check the overrides. Okay, for individual column, what all sway factor and unbraced length ratio has been used. Then we can go to interaction. It will give us the PMM curve.
Okay.
Okay, then we have the details option over here. Details here we'll get all the design summary. Okay, uh, the first tab here will give the design summary,
You can
where all
place
the
it as a
design,
zoom in. We'll just
where all
put
the
like this. If this is put,
yeah, just zoom it a little bit more. You can
yeah.
see it clearly that what all which load combination is the most critical, what are the design moments, okay, and how much rebar area is there, how much rebar percentage is coming, okay, what all additional moments are coming, what is the minimum moment, then it performs the you know the actual compression check as per IS 13920, right? And then we have the shear design, then the joint shear check, and then the beam column capacity ratio. Okay, all these things are checked, right? Similarly, we have the now these. This is a summary. We can check the individual design information by going to say flexural details, where the flexural details are given. Okay, the bending moment information and all that, and the shear details are available in this tab. Then we have joint shear details. Okay, then the beam column capacity ratio. Okay, and then the envelope. Okay, so these things can be checked. Uh, you can check. Students can check this thing manually whether you know
Yeah, but for somebody
getting.
like for this case
Hmm,
only, we are taking rebar percentage is 5%.
yeah, we are getting rebar percentage as 5%.
Generally, we
Okay,
don't give
actually,
above 4, no?
yeah, it won't be above 4. So your section size needs to be revised in this case. Okay,
Okay.
you can
So,
view. You can view.
so it do not give something like pass or fail, that kind of.
No, you'll get a pass or fail over here. You'll get a say a red color line over here.
So
Okay,
that
now
these are all failing means. These red lines. Sorry, I'm not able to hear you.
okay, 6%.
Sorry,
I think.
my connection was disturbed. Can we go again with this discussion? I was asking you what is pass, what is fail, and how to say
Okay,
it.
okay, okay. What is pass? What is fail? So right now, here, if you see that for the columns, if you have this purple color or violet color line over here, and your area of steel is just beside here, so you can see that the member has passed, right? And for if it is red, there is some sort of a failure. Okay,
Okay.
now we don't know exactly what is the form of failure, so for that we need to right click on that member and open this column design information chart and go to details. Okay, in the summary details, you'll get what is the reason for the failure. Right, you can see here that reinforcing required exceeds
Exceeds max
maximum
is
allowed.
allowed. Yeah.
Okay,
Here,
so
how much we are getting? You can go up
here
the
now
report.
you can do one thing. If you see, you can see that it is showing some area of steel, but it is
Hmm.
still failure. It is still a failure. You
Hmm.
can check whether the percentage is exceeding or not. You can go to, you can even view the details over here in the form of percentages, right? You just click on this small arrow button beside this
Concrete
menu.
designer.
You can see here display design info. Then
Okay.
go to display design info. Okay, you can see the design output in the form of total rebar percentage. Okay,
Oh, it is
you
going
can see here
76.
it exceeds 6%, so it is being termed as a failure. Okay, similarly here now you are having some output as OS, signifies it's overstressed. Okay, you can just right click on the column here. You'll find out that this window pops up, and you can see that there are failures for the longitudinal reinforcement as well as for shear reinforcement. You can check in the details. Zoom 100%. Okay, you can see reinforcing exceeds maximum allowed and shear stress exceeds the maximum allowed.
Okay.
Okay, so okay, now earlier while defining column section, we had defined some rebars.
Hmm.
Okay, so that rebar arrangement is used for drawing the interaction diagram.
Hmm.
Okay, we had seen that for beams it was not there,
Hmm.
but for columns it was mandatory.
Mandate.
Okay, so that is used for drawing the interaction diagram.
Okay.
Okay, and the cover that we had mentioned in the define properties page,
Hmm.
for calculating the effective depths. Okay, it's now for beams also we can get this kind of a report.
Beams,
Okay,
what color convention it uses? Same.
uh,
Red. Red
no,
is for fail.
it is this black over here, the black
Black is
thing over here.
pass.
Yeah, black is pass, right? And you can just right click on any one of the beams over here. You can see similar thing over here also overrides. You have the details. Okay, in details we can go to, you can check what all things are being what all design checks are being performed.
But here, what reinforcement it is taking?
Here we don't have any reinforcement initially. Okay, but after, like, whatever after the analysis, whatever results, whatever forces we get, okay, in the form of moments, torsion, shear force, it it calculates an area of steel for that.
Okay, it won't detail the beam.
Yeah, yeah. So here we have, see, you can see here the minimum rebar area, the required rebar area. Okay, okay, and this is the shear rebar requirement. All right.
So
Now
manually
for a
we have
straight,
to take all the values and manually we have to design them or take it into
yes, yes,
Excel.
yes. No, you have the, you get the output. You can see here, you go to plan view, say story 12.
Hmm.
Okay. Now here you see the beam
Percentages
percentage of
requirements, yeah.
steel is being displayed. So I'll change it to the rebar area. I'll change it to display design info. Instead of that, I'll go to total longitudinal reinforcement. So now you see here, this is the top steel requirement. This is the top steel requirement at the midspan. This is the top steel requirement at this joint, near this joint. Okay. Similarly, this is the bottom steel, bottom steel, bottom steel. You can
C for
place
shear.
the cursor. Okay, for shear, we'll go to this small arrow over here, go to display design option, okay, and go to shear reinforcement. Press OK. Okay, you can see here it shows a value. Okay, this is actually in the form of, you can go to the details. Okay, this is actually square per meter.
Okay.
Okay, this is in square per
Per
meter.
minute.
So the values that are being displayed here, that is in square per meter.
Okay. Yeah, it has to be
Okay, so
converted taking the length.
yes, it has to be converted.
Say
You
for
can
just
convert
the
it.
adjacent beam, it is showing 000 B to
Yeah,
C.
that means there is some failure also here. It is showing as a red colored beam, so there is some failure. So there is some failure in the top spool.
Okay.
Okay, in fact, there is a flexural failure.
Hmm.
Okay, that's why it is not showing the results. Okay, guys, you can check the details over here. Okay, say go to 100% zoom. You can check the details here. Reinforcing required exceeds the maximum allowed. Okay, now there is one more thing available for the beam results. You can check the diagrams over here.
Hmm.
Okay, you can check the diagrams. This gives a better viewing
Okay.
experience.
Yeah.
Okay, you can see here the span. Okay, the
Here it
moment
is showing
diagrams.
4 bars. Why it is showing 4 bars here then?
This is a typical thing. This is actually not to be taken
Okay.
seriously. This
Okay.
is just a typical diagram. Okay, and here the moment distribute the sorry, not
Envelope.
distribution.
Yeah, moment
Yeah, the
envelope is
moment envelope is shown here. The longitudinal reinforcement in square is shown. Then the transverse steel is shown in square per meter, and the torsion diagram is also shown. Okay, this can be used for making reports also. Okay, and it is advisable, and it will be a good learning experience for the students as well. When they can go open this details tab and check uh, individually, like
each and every
check each
member.
step.
Yeah.
They can check each and every step
Yeah.
individually and come up with their results,
Yeah.
and also they'll gain some confidence on the software as well.
Yeah.
Okay, so I think I'll just stop for today. Okay, it's already near 6.
Oh, it's already time flies
Yeah.
by.
So, yeah. So,
Okay.
are there any doubts from today's session?
I guess they have to do it on their own
Yeah,
because they might
yeah,
not have
yeah.
followed this. So they have followed till making the RS combinations and checking the
Yes,
drifts,
yes,
checking the whole. But for
yeah,
designer
yeah,
section, they will have
yeah.
to practice.
Okay,
So it will
okay.
be a good idea that they will practice it tomorrow maybe. And
Yes,
after
yes.
tomorrow we'll meet for maybe wind loads and other cases.
Yeah, wind
That's
loads,
it.
and we'll also do some steel design. Okay.
Steel design, if time history also possible, you can tell by maybe El Centro data or any other.
Okay, I'll just give an overview because going into too much depth will not be possible.
Yeah,
It
just give
will
an
take a lot
overview
of time.
how to import the file of time history. No?
Yeah,
If
yeah,
any,
yeah. Okay,
any time history data is given, how to import it and how to create a load case of it. Other
okay,
things are
okay.
for research, and those purposes we will fulfill over here. Just
Yeah, yeah.
tell us the module options. So
Okay, okay.
it was a good session, but it
Hmm,
requires again a change of habits which we are used to design to check all of these things through the
hmm,
frame,
hmm.
the references which ETABS is using.
Yes.
Because generally, what we do is we put it in RCDC or some other these kind of softwares. There
Hmm.
you can change the section very quickly. Here we have to change the section again and then recheck for each and
No,
every.
here there is an option in ETABS that you
Hmm.
can see. Actually, if you right click over here,
Hmm.
okay, you can go to overrides, right? You see here current design section is 5. Sorry, B
3050.
3. Yeah, you can change that from here. If you have some other sections defined over here, okay, you can change that.
Okay, then it will again run whole sections.
It will like if you have the analysis done over here, and
Yeah,
say you have 2 or 3 more sections already defined with you,
defined.
you can change it. You can change it, and you'll see the values will automatically change for the design.
Okay.
Okay, not for the analysis. The analysis results will remain the same.
Yeah.
but your design will change.
Design
Your design
designs
value.
will change.
Yes.
So this is the detailer which you are talking about, or detailer is again a
No,
separate
no.
module?
Detailer is a separate thing. I think I'll show that in the next class.
Okay.
Here, I think we have this beam bar selection and the curtailment rule. Okay, then all these things need to be explored.
Yeah,
Okay,
we can do it
okay,
sometime
then.
with detailers also.
Yeah, yeah, yeah. Okay, this is not actually, this can be done on your by yourself also, but I'll
Okay.
still give an overview.
Yeah, you can give.
Okay, yeah.
All right, and
Okay, then we'll stop for today.
yeah, sure. So thank you so
Okay,
much once again
okay,
for this detailed
yeah,
session. We'll meet tomorrow at 4. All of us
yeah,
will join
okay,
at 4.
sure,
Thank you so
sure.
much.
Thank you, thank you.